What's up, Honors Algebra 2? Today we're going to take a look at even and odd functions. We're going to look at how to test for them and what that means in terms of the graphs of these functions. So real quick, you can copy this down into your notes as I highlight some of the information. Even functions, there's a specific test we need to do to test if something is an even or an odd function. Both tests start out the same way. We simply replace all of the x's with negative x and then see what happens. If we do that and we get the original function back, it's an even function. And if we replace all the x's with negative x's and then we get every sign reversed, we will call that an odd function. And even functions have symmetry with the y-axis, odd functions have symmetry with the origin. And little examples of how these look, I did draw some doodles right here, and I'll also show you some information about this and try to bring it to life a little bit. But again, you just want to copy down the basic gist of this. So the x squared graph, the parabola, you can clearly see it's got that symmetry with the y-axis. That's a little bit easier to notice. And to run the test, there you see, I replaced the x's with negative x. And when I squared the negative x, I got the original function back. So when that happens, like I said, we call that an even function. And to test this new function down here, I replaced all the x's with negative x's and simplified. And what happens is I actually got all of the signs to be completely opposite. First term was positive, now it's negative. And the first term was negative, now it's positive. So it seems as if this has just been multiplied by negative. And that is the conclusion of the test. Funny story, you actually have a picture of this function on page 7, number 14 in your notes. Okay, but like I said, I'm going to try to bring some of this to life for you. So let's take a look at that parabola in a little more detail. So I have the y-axis highlighted, and you can clearly see if I were to maybe fold the paper over onto itself, the two sides of that parabola would align. And really what it means when we say f of negative x equals f of positive x, it means every time you have a coordinate pair on the graph, I wrote a couple actual ones and I wrote a generic one, x comma y. That also means you would have negative x comma y on the same graph. And you can see that with the samples I've shown you. 2, 4 and negative 2, 4. 1, 1 and negative 1, 1. They are both on that graph. When we go to look at that other equation, x cubed minus 4x, like I said, testing for symmetry at the origin visually, unless you know what you're looking for, it's kind of out there. But I think we can make it seem a little easier to understand. First, just again, review the algebra. You do see I've replaced all of the x's with negative x's, and I've gotten the complete opposite of the original function. So what that does mean is every time we have a generic point on our graph, you know, again, say x comma y, well, that means we will always have a different point on the same graph where the x value is opposite and the y value is opposite. And that is true for every single ordered pair on the graph. When you have one xy, you have negative x and negative y together. And so let's talk about what symmetry about the origin means. And as I said, that's kind of funky. But what you want to maybe think about is rotation, all right? So I'm going to maybe hold my finger right here on the origin, and we're going to spin the paper around 180 degrees. So I want you to kind of remember how this graph looks. You know, it rises, it falls, it rises. And now I'm going to do the spinning. Here we come. And actually now, look at that. What you see is the exact same graph. It rises, it falls, it rises. So that's one way to kind of wrap our heads around symmetry about the origin, just hold your finger on the origin of the graph, spin it around, and you get the same picture. There is another way to think about it, and it is in terms of a double flip. We're doing some gymnastics here, a double flip. So what I mean by that is, well, we're going to, doesn't matter the order, but we're going to maybe take this graph and first flip it over the x-axis and then flip it over the y-axis. Or if you're feeling crazy, reflect it over the y first and then the x. So if I just do a little sketch here, I'm going to reflect this over the x-axis. So whatever is down here, I'll show up here. And whatever is up here, I will reflect down to here. So what I'm going to get is something, again, just real rough sketch. But if I reflect it over the x-axis, I'll get what I've drawn in pencil. Now I'm going to take my temporarily reflected graph, which I've drawn in the pencil. Now I'm going to reflect it over the y-axis. So whatever's on the right side will flip to the left, and whatever's on the left side will flip over to the right. And as I do that, my friends, what you see is that I'm now drawing that double flip on top of the original shape. And that is another way to visualize symmetry about the origin. So again, you've got either a rotation, 180 degrees about the origin, or you've got the double reflection. All right, so either way that you're more comfortable with, that's something you can do to wrap your heads around what these graphs look like with the symmetry and the origin. Okay, so let's practice a few algebraic examples here of just testing for even and odd functions. We're going to determine what function is even, odd, or neither, and then we're going to kind of fill in what kind of symmetry would each graph have depending on the outcome of that test. So to start off the test, first thing you're always going to do is throw in the opposite of x before you do anything else. And then based on the outcome of that, you'll make your conclusions. So we have m of negative x, a of negative x, t of negative x, and h of negative x. Oh, look at this math. And let's see what we've got. All right, so we know how to put things into functions. We can set up the template for each function and then feed it the new input, negative x each time. All right, let's follow order of operations. I'm going to take negative x and square it. Negative x times negative x is positive x squared, multiplied with the 3 gives me 3x squared. All right, negative 5, negative x gives me positive 5x, and lastly, plus 1. All right, so let's examine this. We have to now look at the original and look at our answer and decide, are they the same, are they exactly the opposite, or are they neither? And I think we'd have to conclude, well, the first and the last terms are the same sign, but the middle term is a different sign. So this is not, oops, not f, this is not m of x, nor the opposite. I wrote that very not nicely, but it is not negative m of x either. So this function is neither even nor odd. It does not have symmetry with the x-axis or the origin. It might have other symmetry. In fact, it does, but it does not have the two types we're looking for. All right, let's try number 2 here. And get that template set up and input the same thing each time. And if we do that, let's see, order of operations again, negative to the 5th power will come back out negative x to the 5th multiplied by 5 gives me negative 5x to the 5th. And let's see, negative x cubed is negative x cubed times negative 3 is positive 3x cubed. Okay, well, let's compare. So a of negative x is this. I could already tell it does not match the original function, but does it match the opposite of a of x? In other words, if we were to multiply this function through by a -1, turns out, everybody, exact match. So what we are looking at here is an odd function. It fits the definition. A of negative x is exactly equal to the negative of a to the x. And this graph, if we were to draw it, would have symmetry with the origin. Okay, let's try this test out a couple more times and just make sure we are settled with it here. Something like number 3, t of negative x. Okay, we're getting to be pros at this, I hope. We set up the template for the function. Here's our negative x. And following the order of operations, what I would do first is raise negative x to the power of 10. When I multiply this negative thing with itself 10 times, it becomes positive. And multiply that by 7, we get 7x to the 10th. Same issue happens over here. We take the negative x, power it up 6 times. That becomes positive x to the 6th. And then times 9, negative 9 rather, is negative 9x to the 6th. So look what we've got. We've got an exact match. First term matches, second term matches. What we did algebraically, we swapped out x for negative x, but the math mathed in such a way that it came out back to the original function. So surprise everybody, it's even. And if we were to graph this function, we would see it has a symmetry with the y-axis. Hooray! Okay, one more little test for us to do. H of x equals the absolute value of x. Same idea as before. Get the template of the function set up and feed it the new input. Well, anyone who knows anything about absolute value is going to realize the absolute value of negative x is, of course, the same value as the absolute value of x. They're going to be the same sign in the end, which is positive. So algebraically, we have thrown in the negative x where the x is. What came out of that after we did all the mathing is the original function. So h of negative x equals the original function. So once again, my friends, we're looking at an even function. And this will again have some symmetry with the y-axis. And just as a little added bonus, I think a lot of us remember this shape here from Algebra 1, V for value, V for victory, and we'll be seeing that shape certainly in the future, but it's definitely symmetrical with the y-axis. All right, that's all about even and odd functions. Ta-ta!